Hello community! Today we do some extreme grokking and maybe we can get rid of rag finally. So let's have a look. Now we ended part 2 here with this outlook and we have a look why grokking works out of the box here for the task of a comparison. And then finally we compare grokking GPT to our GPT-4 Turbo with a rag system and we have a look what is a better performance system. But at first you remember there was a part 1 of this series where I showed you here this particular visualization. It was about understanding grokking in the representational learning space, and I showed you that there are geometric figures appearing here, especially if you have here the 2 principal components here of a learned input embeddings, and you see this, and we had a look at an addition function modulo 12, think about it, and you have here your analog clock. And you had a lot of questions. Hey, how is this possible? And is it really that simple? And the answer is, of course, it is not at all simple. So let's have a look and answer your question first. June 3rd, 2024. There's a beautiful paper on the geometry of categorical and hierarchical concepts in LLMs. Have a look at this and they say, hey, how is now the semantic encoding in our representation space? And what about if we have more complex concept that we want to encode? And they have a beautiful, rather mathematical explanation. And they start here with a linear representation hypothesis, which suggests that the semantic concepts are linearly encoded within the vector spaces of LLM. And the binary concept, for example, let's say a counterfactual pair like male versus female, they have a well-defined linear representation as a direction in the representation space. And the aim is, of course, to understand how the geometry of a representation space encodes now the relationship between the different concepts. And a concept can be easy: plant, animal, or reptile, bird, fish, mammal, or elephant, tiger, dog, whatever you have. So those are very simple concepts, and we want to see if they are constructed in a way that in a specific vector space, they are really compartmentalized into their region in the space. You see here, for example, here we have all the birds, here with all the fish, here with all the mammals, and you get the idea. So now let's have a look at this. Now we have to look back in November 2023, and there's a beautiful publication here, University of Chicago, the linear representation hypothesis and the geometry of large language model. And they introduced here a simple mathematical function that I need, and this is called a causal inner product. Causal inner product is beautiful visualized here. You see, this is what we want. We want a causal inner product. This means a linear transformation of the representation space such that a causal inner product becomes an Euclidean form. And you say, well, of course, this is simple, and you're absolutely right. However, the high-level strategy is to show how to represent binary features, plant, animal, as vectors, to show how geometry encodes semantic composition. And then use this to construct a representation of much more complex concepts, like, for example, here, fish, bird, mammal, reptile, and so on. So, you see, there is in this publication just a little bit of mathematics and just a little bit of 8 mathematical theorems and just a little bit of some pages, yeah, a little bit of more mathematical pages. But they were able to construct here the transition. So we have now the power of having a vector representation of these concepts. And this is beautiful. So that now we can use an ordinary, it's not such an ordinary vector space, operation to construct representation of other concepts. So you see, this is beautiful. But now the mathematical space that we're operating is not that simple as some of my reviewers think or some of my subscribers ask me. However, this illustrates the geometric relationship between various representation vectors. Now we have vectors, and the main takeaway is that the semantic hierarchy is encoded here in an orthogonal system. And as you can see here, if you have more and more, they try to be here orthogonal to each other, and this is here our first theorem that we started from. And if we go on and we make it a little bit more complicated and a little bit more on a categorical concept, you say, how do we do the representation of the categorical concept? And you say, well, of course, there's a beautiful solution, and this is via a mathematical synthesis. And here you have some example. And if you still dare to ask, what is a simplicial complex here in a graph neural network, you remember I have here this beautiful video. And yes, I'm sure that all of you have seen it. If not, here two definitions of a polytope representation of a categorical concept and the theorem 8 here, the last one where I showed you a little bit of mathematics, the representation of a categorical concept as simplices. So we do have the mathematical tools to understand this now. So beautiful. Let's have now a geometric summary just to answer your question. So categorical concepts like mammal, bird, reptile, fish are geometrically represented as now mathematical simplices in the representation space of LLMs. And this means that simple categorical concepts are mapped now to geometric shapes whose vertices correspond to distinct categories within a concept. As I showed you, these hierarchical relationships, and you say, hey, hierarchical relationships, this was in video 2. Yes, absolutely right. And now encoded through this orthogonal feature. And this ensures that the changes in the representation of one concept do not interfere here because we have an orthogonal concept. And if we go a little bit more complicated, if we go beyond binary categorical representation, we find ourselves now in the area of complex concepts that are represented as polytopes. And you might say, yay, mathematics, I do remember. Yes, it was so beautiful. Yeah, a polytope here is a construct from direct sums of simplices corresponding to each category, reflecting the hierarchical relationships and the complex semantic structure of our human sentence. And yeah, this is all about here our human language. Now, talking about simple, I have to tell you I made a little bit of an oversimplification, but now you're absolutely right. We have to go back and let's have a look at this particular mathematical space, because it is not a simple space. It is a canonical representation space. So here we go, ladies and gentlemen. The canonical representation space refers to a version of the model's embedding space where the dimensions have been standardized and normalized in a way that the geometric property, like distances and angles that we have here, directly correspond to the semantic relationships. So that means the space is canonical in the sense that it represents a standard or ideal form where the embeddings are adjusted to reflect to the clear and interpretable relations such as the semantic similarity or a hierarchical structure, semantic similarity, cosine similarity product. You know all of this. And now you ask how we do this, and the mathematic folks between you say, hey, we have the widening transformation. And you are right, this is a specific statistical technique applied to achieve the aforementioned canonical state. Two main steps, decorrelation and normalization, simple. And if we do this here and we transform here the embedding vectors, the complexity of the embedding tensor structure such that the covariant form, the covariant matrix becomes the identity matrix, which is the key characteristics of all canonical representation space things. Wasn't that simple? Now, if you read this particular publication here, you might find that they use the phrase applied to the unembedding layer. And when I first read this, I said, hey, what is an unembedding layer? And then I said, okay, it must be the output layer or a classification layer, which converts here the final high-dimensional vectors back into the output tokens for tasks like language generation or in other forms if you have, for example, here a downstream task for classification. So this means by applying here the widening transformation to an unembedding layer, now the researcher aimed to make the final actionable embeddings as semantically transparent and geometrically interpretable as possible. And this now facilitates a much deeper understanding and, yes, maybe a little bit better manipulation of the model outputs. So you see, simple mathematical transformation, but not such a simple mathematical space as some of you guessed in your questions. So here we are, and all my eagle-eye subscriber noticed, hey, wait a second. He was just talking about the final transformer layer, and you are absolutely right. This technique only works here at the very end, at the final layer. But in video number 2, I showed you, hey, we have two methods where we can probe each layer in our transform architecture to understand here the reasoning pathways, the generalization circuit, like I showed you here in part 2 of this mini-series, in our LLMs. So now we have different tools, but today we will focus here, of course, here on grokking Grok transformer implicit reasoner, and we look here at the second different task that we had not the time to have a look in video number 2. And this task is called comparison. And as I showed you, we have a sentence 1, a person has a specific age, a second person has another specific age, which of the person is younger? And I've showed you, if we look at accuracy, and we have here our optimization step, this is where grokking is happening here. You see for the training, in distribution, beautiful. For the test, in distribution, beautiful, 100%. And now the beauty is here also for the test out of distribution data, we reach here close to 100% accuracy if we do grokking on a task like a comparison. Let's build now our configuration and let's see how it works. I showed you in part 2 that we open up the black box of a large language model, and now we do the same. And now we focus on a simple task, comparison. 2 sentences, and the LLM should be able to do a comparison. Of course, we later look about 1,000 sentences, and we do a comparison between 10,000 sentences. But for the moment, we are simple. We build a simple configuration. So we compare the attribute values of entities. And in our first try, we say, hey, we have about 1,000 entity in our graph. We have about 20 attributes and 20 ordinal values for the attributes. And each attribute has a specific label space, which is a set of relations specifying its comparative form. Less than, equal to, bigger than. And if we have the attribute age, for example, this label space would translate into younger, contemporary, or an older person than. So you see, simple, trivial. Now you remember part 2, I showed you the atomic facts and the inferred facts. So the atomic facts here now are again our triplets. The triplets are entity, attribution, and value, where we assign a random value for each entity and for each attribute. And again, we randomly partition the atomic facts into atomic in distribution and atomic out of distribution in the ratio 9:1. Great. Now, you remember we used here 2 specific tools to probe each and every layer of our transformer architecture. And it was, as I've shown you in detail in video number 2, logic lens and causal tracing. Logic lens, we looked here to interpret the activation within the transformer network, and the causal tracing helped us here to map out the causal pathways within the network, to see which components are critical for specific reasoning paths and outcomes. Let's talk about scientific notation for a second. Whenever you see in the literature S7a, this means it represents a hidden state in the 7th layer of our transformer model for the token corresponding to attribute A. So in this particular stage, the hidden state S7a contains here the processed information about the attribute A after it has passed through 7 layers of our transformer architecture. And if you have for entity, you have S5E1, it is really similar. This represents a hidden state in the 5th layer for the token corresponding to entity E1. It contains all the information about the entity E1 after processing through 5 layers of our transformer architecture. So you see, the notation is explained. And here are the results. Let's have a look. On the left side, we have the in-distribution accuracy, and on the right side, we have the out-of-distribution accuracy for different values of phi. Remember, phi was our ratio of inferred to atomic. And as seen in my last video, this is a very sensitive parameter for the performance of our grokking, how fast grokking and how good grokking will happen, how fast we reach here 100% accuracy. So if you see here an in-distribution accuracy with a phi of 3.6, we are just starting here at 80%. Yeah, slowly we go to 85%. Yeah, then slowly 90%. So it takes time. But if we have a phi of 12.6, we just jump, and 100% accuracy, and this is done. Great. And again, OD, the same. If we start here with a 3.6, we're here at 80%, we wait at 80%, and we reach 85%. But if we increase here the ratio phi, yes, we are here at 100% for OOD accuracy. And this is the beauty. This is here this beautiful thing of grokking. Okay, So now we're gonna open here the black box of the LLM and we will examine the model's internal workings. And we want to explore if it will reveal here also a generalizing circuit now for the second task of comparison. And of course, we do this on a grokked transformer. Let's start. Beautiful. So we have the label space preparation. As I showed you, the model prepares it a label space from attribute A and stores it in, now you know it, in the hidden layer 7. Then it's retrieving the atomic facts. Interesting. In the lower layers, let's say 0 to 5, the model retrieves the 2 atomic facts and stores those attribute values V1 and V2 at the lower levels. Here you see the hidden layer 5. And then we have the task of comparison here, plus label fetching. And now in the upper layers, 5 to 8, the model compares now V1 and V2 and fetches the appropriate level. You know this here, smaller, equal, or bigger than, from here our hidden layer 7a based on the comparison result. So unlike that we have this generalizing circuit from the composition task, in the comparison task that we look now, the atomic facts are retrieved in parallel. And this is the beauty. We work here in parallelization structures, indicating that they are stored also solely in the lower layers. Remember in video 2, we had a problem here with this, but now we understand where the atomic facts are stored in the lower layers and where, if you want, a higher intelligent function like comparison is happening. This is happening in the upper layers, like we would expect it in a grokked transformers. And of course, we used here again here our 2 methodologies of causal tracing and logit lens. So causal tracing, again, traces how the attributes and the entities are processed and how their relationships are formed and used in the model reasoning process if we go through all the different layers of our transform architecture. And the logic lens helps here us to interpret the contents of the hidden states. Beautiful. For my green grasshoppers, just to read, this is again a short summary of the hidden states. And this, for my green grasshoppers, here I show you again the mechanism of out-of-distribution generalization that is now working, remember, for the task of a comparison. And here I give you the 4 steps in a short summary: parallelization, retrieval of the atomic facts, uniform storage in the lower layers, the formation here, takes a little bit of time, but then we have a formation of a generalization circuit and the causal strength and the accurate prediction by our grokked transformer. So again, you will see, hey, but this is the same. Yes, absolutely. So in our task 1 and task 2, we have the same pattern emerging. Initially, when the model starts to learn, when we train this model, we have that the model is more or less memorizing here the specific training examples to make a prediction. So we have here, we see, if we open this black box, we see specific memorization circuits happening active in our transformer architecture. But over time, with enough training iteration, if grokking sets in, we see now in our neural network structure that a generalization circuit is taking place, and now also for the task of comparison. Great. For my green grasshoppers again, task composition, task number 1, task number 2, comparison, where we focused today. Parallel processing, this makes it so beautiful. But now I know you have waited for the performance benchmark. What is a grokked transformer able to do? How good is it if we compare it here with a GPT-4 Turbo or Gemini 1.5 Pro? And remember, our little grokked transformer is a little tiny transformer. 8 layers, hidden dimension 7, 6, 8, and only 12 attention head per layer. So, and it has to fight against a Gemini Pro 1.5 trained on how many trillion token? So you see, now what we need is a beautiful test configuration. And the authors here said, hey, we have a very specific test. And of course, it is not really a simple test. It is tests here the antisymmetry and the transitivity of a specific comparison of our parameters. And we have some added facts that make it not that easy, but in theory it is also you just answer a test query. where our LLM would just successfully locate two in-domain bridge entities, which can connect the two queries entities into a mathematical proof that gives us then the relation. That's all there is. Well, however, the author thought about this and said, hey, let's not make it too simple. So here we go. You have here two query entities, John and Rick. And then you have those bridge entities, in our graph, Sam and Mia. And then, simple, that John is younger than Sam, and Sam has the age of 10, and Rick is older than Mia, and Mia has the age of 13, and you get the idea. Now, as I told you, we increased the difficulty a little bit because each query entity, like John, connects now to more than 50 facts, and each bridge entity, like Sam, connects now with more than 900 facts. So it is not as simple as you see it here in this publication, but this is a much, much more dense and complicated graph structure. So you see, or you might argue, hey, this is not fair. You have here real complicated tests and not such a little wish-wash simple test that we use normally to test here for causal reasoning. Yes, we know. But now we have a real powerful tool, a Grok transformer. Therefore, we can dare to go to more challenging causal reasoning tests. And we don't have to stay here in the kindergarten area for causal reasoning. And here are the results. The authors did this, and they did it with a direct answer prediction. And Gemini Pro 1.5 gave us here close to 30%. And then they say here, okay, now we combine here with chain of thought with verbalize here your reasoning step. And Gemini 1.5 did an 11% accuracy on this task in this configuration I just showed you. Now, this is not really famous, no? If you think that the normal threshold is about 33%. And then they said, okay, no problem at all. We do now with retrieval. We have a RAG system, we have a retrieval, and augmentation and beautiful. And they said, okay, so for Gemini Pro 1.5, it is now 37.3%. And you say, wow, yeah, it is now about the threshold of randomness. Yeah, 4 percentage points, okay? And then they said, okay, but now let's take another system. And they took GPT-4 Turbo with a retrieval system, and they reached exactly 33.3% accuracy, which this is the time where I had to smile a little bit. And then I said, okay, but now we bring in the heavy weapons. Now we have a chain of thought, reasoning, plus here retrieval from our RAG. And now I will show you here the perfect performance. And Gemini Pro 1.5 reaches now 12% instead of 11.3%. And you might say, wow, this is really that it shows us where we are currently with our standard LLMs. And our GPT-4 Turbo reached 31%. Okay, well, the authors did this and they came to a conclusion. And here I have here the official unaltered statement by them. And they said, hey, all LLMs, all models based on non-parametric memory, RAG, fail badly. Where the only settings that surpass here the random guess at 33.3% is with the retrieval augmented settings. Around this, we reached here 37.3%, and you say, wow, amazing. And with GPT-4 Turbo, we're exactly on the threshold. So, okay, this is why they say, hey, non-parametric memory, so additional retrieved memory fail badly. And they say LLMs perform worse, especially Gemini, when prompted to reason verbally in a more complex causal reasoning path. And they say we find that this is because the model tends to give up and decide that the query is not answerable after some search steps. Shockingly, most of the chain of thought rationals were wrong due to either hallucination, underivative facts, or logical errors. And none of them can lead to the answer. Now, if you say this is a little 7 billion something, from Mistral, okay, but we are talking here about Gemini 1.5 Pro and GPT-4 Turbo, so these are really powerful, some mighty LLMs, and they failed significantly. And the authors came to the conclusion, this illustrates the current model's inability to reason deeply with non-parametric memory, means RAG systems. Great, this is the state of the art here of June 2024. And now I know you're interested and you say, hey, okay, but our grokked transformer, do we reach? And now you look at this and say, hey, what about 50%? No? Okay. Now let us dream, what about 55%? Well, maybe we can go up to 57% if it's a sunny day. And if you want to know the truth, well, we reach 99.3% with our grokked transformer. And you remember, in the search base, each query entity we had more than 50 facts, and each bridge entity is connected to more than 900 facts. So this is really a challenging task. I know, and the authors notice this. This is not this simple test that we have, but we want to go to real LLM reasoning. So there you have it. What is the final verdict here for reasoning and generalization? The grokked transformer is trained to compress and integrate information effectively, enabling it to perform complex reasoning tasks with high accuracy. 99.3% is good. And the authors say, in contrast, models like GPT-4 Turbo and Gemini Pro 1.5, even with advanced prompting techniques and retrieval mechanisms like RAG, struggle with the reasoning depth required for these tasks. And the study suggests that non-parametric, memory-based models, such as GPT-4, are currently limited in their ability to reason deeply and systematically without significant improvements in the architecture. Now, for June 2024, this is quite a strong statement. No? We are not anymore in 2023. So, therefore, this gives us a new insight. And this gives us a new direction for our research. Yeah, for my green grasshoppers, just to be sure, parametric knowledge is embedded within the parameter. This is the weight tensor structure of our model during the pre-training. This is directly learned, for example, then during fine-tuning, from the training data and encoded into the neural network architecture. And this is capable of generalizing from training data to unseen data, as I just showed you, especially with grokking. Yeah, with grokking, it's of course beautiful. Now, non-parametric knowledge is not embedded in the model parameter, but instead stored externally and accessed as needed, a RAG system. This involves mechanisms like retrieval augmented generation system, where the model retrieves the relevant information from external databases. Non-parametric system can scale beautifully by simply adding more data to the external source without altering the architecture at all. And both parametric and non-parametric approaches have their strengths and weaknesses. And before I read this study that I showed you in this video, I would have agreed with this sentence. Combining both approaches can potentially leverage the strength of each LLM. But today, knowing what we know now, I think this last sentence is not valid anymore. Let's have a look at this a little bit later on. And I know what you ask. You say, hey, this grokking, this is nice. Does grokking work on all kind of neural networks or even beyond neural networks? And here you have a study here, Computing and Cybernetics here, College of Engineering here, Australia, an empirical exploration of grokking that goes beyond neural networks. This goes into the topic of complexity research, model complexity. And they show that we have it also over there. And I know some of you asked me about Kolmogorov-Arnold representation. And yes, we have grokking even there. And there's here this publication I would personally recommend to you if you want to know how you can accelerate the grokking in learning arithmetic operation via Kolmogorov-Arnold representation. And for my green grasshopper, this is not such a complicated thing. Kolmogorov-Arnold representation theorem stating that every multivariant continuous function can be expressed as a superposition of two functions. That's it. That's all there is to it. And there you have it. Some extreme grokking happened today. We built grokked transformer and we compared their performance to the latest and most powerful LLMs if we combine them with RAG system, and we saw that the grokked transformer outperformed every other LLM plus RAG system on this planet, in particular task of causal reasoning, of real complex causal reasoning. And I think that this research points here the way forward. I hope you enjoyed it. I hope you found some interesting new facts in this video, and it would be great to see you in my next video.